Hello everyone, my name is Maggie Tansky and today I will be walking you through my report for Lab 3 Black Hole Orbit. In this lab, we will use GlowScript to analyze the motion of a star in relation to a black hole of unknown mass located at the origin of our coordinate system. We are making the assumption that the net force on the star consists solely of the gravitational force of the black hole acting on the star. We know the mass of the star is 2 times 10 to the 30 kilograms, and we can use GlowScript to compute the net force as well as the position vector between the two bodies. Therefore, we can rewrite the equation for calculating gravitational force. Force of gravity equals g times mass of the star times mass of the black hole over the position squared, as the mass of the black hole is equal to the force of gravity times the position squared over g times the mass of the star to solve for the mass of the black hole. The GlowScript code uses our GT email address to generate a series of x and y coordinates for the star. So I updated the system properties and data, setting the mass of the star to be 2 times 10 to the 30th kilogram and the delta t to be 86,400 seconds, aka the length of one Earth day. We will use calculus to determine the star's velocity in the x and y directions using the position data generated by the code. In the main calculation loop, we define the initial and final velocities as vectors and use them to calculate the star's change in velocity. Next, we will use these initial and final velocities along with the star's mass to calculate the star's initial and final momenta, which we will use to find the star's change in momentum. Next, we divide delta p by delta t to find dp dt, the rate of change of momentum over time, and define f net as equal to dp dt. The unit vector for the star's momentum is found by dividing the initial momentum by the magnitude of the initial momentum. Next, we find d magnitude p over dt by subtracting the magnitude of the initial momentum from the magnitude of the final momentum divided by delta t. Next, we multiply d magnitude of p over dt by the unit vector to find the parallel component of dp dt, which is equal to the parallel component of the net force. Finally, we find the perpendicular component of dp dt by subtracting the parallel component from dp dt, which is equal to the perpendicular component of the net force. We can also compute the magnitude of the position vector from the center of the black hole to the center of the star. We tell the program to print magnitude of position vector and the magnitude of the net force. And when we run the program, this is what we see. We can then gather that the magnitude of the net force is 1.738 times 10 to the 29th newtons, and the magnitude of the position vector is 1.18191 times 10 to the 13th meters. We can then plug our data into our formula for the mass of the black hole, which we find to be equal to 1.8811 times 10 to the 35 kilograms. Now, imagine the black hole whose mass you found was removed, and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found of the original one? No, because the momentum of the star remains the same. Therefore, the mass of the black hole must be very close or equal to the mass of the original black hole.